Welcome to the Tactics Project Lecture Series on Research Methods. I'm Ahmet Ademoğlu. I'm a faculty member at the Institute of Biomedical Engineering, Boğaziçi University. The first lecture in our series is about science. In 2018, a short critical perspective was published in Nature by Gundula Bosch, a researcher at Johns Hopkins University. Her main point was that many PhD programs, especially in the biomedical sciences, were structured on turning students into narrow specialists instead of broad critical thinkers. She reminds us that the PH in PhD stands for Doctor of Philosophy, which implies that doctoral training shouldn't be just about mastering lab techniques, it should also be about thinking deeply on science. She believes that a proper scientific training should allow researchers to recognize how errors can occur in research. They should be able to understand the scientific process with a critical mind. Because of that, students need to tackle the bigger picture and consider things like ethics, logic, and the relevance of their work to society. They should also be able to explain their research not just to other scientists, but also to regular people, which requires to attain a broader perspective on science and its relation to life. That's exactly why we start today by trying to understand what science is all about. What are the big questions formulated around science? We know that there are certain disciplines that search for answers to these questions. For instance, what is the origin of science? How did it evolve from the natural philosophy in the ancient and medieval age to the modern science today? Why did the modern scientific revolution happen in Europe in the 17th century instead of any other place or any other time? These kind of questions are answered by the discipline we call history of science. What about the questions as what is scientific method and how does it differ in various disciplines? How does scientific knowledge differ from other forms of knowing? How is it related to nature and reality? These are the kind of questions that philosophy of science studies. On the other hand, sociology of science is asking questions like how is science related to the disciplines as philosophy, metaphysics, theology, and law? Why some countries or regions are more successful in scientific performance than others? What are the benefits and problems arising from modern science for the individual, the society, and the nature? Finally, we have the policy of science asking questions like how does science affect politics, economics, and social development? What are the correct policies to enhance scientific progress leading to economic development? How can science serve for peace and sustainability? Let's talk about the dual character of science a little bit. Science has always had a twofold character. One, natural philosophy. Two, instrumentalism. In parallel with this dualism, the ancient Greeks used to have two key terms. The first one is episteme or scientia in Latin, was asking the question of why and looking for an answer to explain the meaning of reality and to determine the absolute truth. On the other hand, the second term was techne or ars in Latin, was the knowledge of doing practical things like ships, wooden articles, etc. The word technology that we use today comes from the word techne. The word artificial is from the word ars. Therefore, as an intellectual as well as a technological enterprise, science is about to build existential and metaphysical formulations for determining humans' place in nature on the one hand, to develop methods and principles to understand and to control nature for the security and welfare of human beings. What is the relation between this philosophical dualism and the nature of scientific knowledge? If you look at these words in the list, like theories versus facts or ideas versus sensations, We can easily see that the first member of each pair comes from our minds, whereas the second one comes from our external world. The first is more abstract and conceptual, the second is coming from pure observation. These pairs refer to a distinction between the unobservable and the observable, and a distinction between the speculative and the empirical. So how does such a dualism shape the scientific knowledge? In ordinary language, all statements are either analytical or synthetic. When we say all bachelors are unmarried, the first part of the statement is semantically equivalent to the second part. In other words, the second part does not say anything additional about the bachelors. These kind of statements are called analytical statements. When we say all bachelors are unhappy, the second part of the statement gives a qualification about the word bachelors. These kind of statements are called synthetic statements. On the other hand, all statements are either a priori or a posteriori. The knowledge which is independent of experience is called a priori. It is acquired without any experience. In contrast, a posteriori knowledge is something known only by experience. When we say 1 liter of water added to 1 liter of water gives us 2 liters of water, this is an a priori statement. But when we say the water boils at 100 degrees Celsius, this statement claims something about the external world, which we can only retain by experience. What about the statements like everything that begins must have an end, or every effect has a cause? They say something about the world, so they are synthetic, but they are accepted as true without doing experiments. German philosopher Kant calls these kind of statements as synthetic a priori. Let's have a look at the hierarchy of scientific statements. At the very bottom, we can have an assumption or a guess that is not supported by observation. This is called a conjecture. If a conjecture is formulated based on some observation, then it is called a hypothesis. Therefore, a hypothesis is an assumption about a certain event. A theory is a belief or a hypothesis that has been around for a long time and has accumulated a great deal of evidence to support it. A theory is a hypothesis that is closer to truth. When a theory has gained common acceptance in the scientific community, it becomes a principle or a law. In addition to these grading concepts, we have some others. For instance, a fact is an empirically verifiable observation accepted by everybody as true for practical purposes. An axiom is a statement that is accepted as true without proof. A theorem is a principle inferred from other axioms or principles using deductive method. A model is a system of postulates or inferences used as a conceptual description of a system. Sometimes a model is vital for us to make sense out of the observations. What are the methods of obtaining scientific knowledge? One method called deduction goes from the general to a specific. As an ancient Greek invention, it is the first systematic approach to reasoning. It is a speculative process of reasoning from a general assumption to a specific application. As an example, all things have a destiny. For instance, let's take the stone. The stone belongs to the earth. Therefore, when it is free, it falls down the earth, which is its destiny. The other approach is just the opposite way of deduction. It starts with a specific assumption based on observation and reaches to a general conclusion after performing a series of experiments that support the assumption. In modern science, we use the combination of these two methods. We start by proposing a hypothesis or a question by examining facts obtained from observation. Then we develop a general conclusion, leading perhaps to a theory according to the strength of evidences. Once it is there, we try to deduce the probability that This theory is false by empirical evidence. This is the so-called inductive deductive or hypothetical deductive method. Let's say we have a scientific phenomenon. How do we analyze its complexity? Basically, there are two opposing processes. One of them is called reductionism. It is to reduce a complex natural phenomenon into its fundamental parts and studying their interactions under fixed conditions. Scientific reductionism is based on the notion that everything in the universe can be broken into smaller chunks and the whole can be understood this way. This is also the so-called analytical approach introduced by the 17th century French philosopher René Descartes. It is also referred to as Cartesian reductionism. If we know the parts, the dynamics of the whole can be explained. However, a major problem with this approach is that sometimes it is not possible to go back to the whole by just fitting the findings. For instance, let's assume we can explain almost everything on a molecular level in the brain. Yet, we may not be able to explain how a single neuron helps composing a poem. The rejection of this approach is called holism. Its fundamental rule is that the whole is different from the sum of its parts. Instead of dismantling it and studying its parts, holism inquires a system as a whole in its entirety. In fact, science relies on both reductionism and holism. We can dismantle a complex system into various components to get first-hand information about it, and then we can put them back together within a meaningful context to have a full understanding. What are the fundamental set of assumptions that allow us to know about the world? What makes us think that we can know about an external event in an objective sense? It is the positivist worldview that makes it possible for us to make such assertions. As a philosophical theory developed by the French philosopher Auguste Comte in the early 19th century, positivism asserts that reality can only be understood through scientific inquiry by discovering the natural laws governing it. It also assumes that the world can be understood with human comprehension in an objective way. Any statement which cannot be verified by the experiment is not acceptable as knowledge. Therefore, the scientific method, which is based on experiment and observation, is the only way to attain true knowledge. The methods are usually hypothesis-driven, findings are generally quantitative and statistically significant. The results are generalizable to a population beyond a sample through the positivistic approach. Based on its positivistic assumptions, the modern science was traditionally based on the maxim of verifiability, which means a scientific statement should have to be empirically verifiable by conducting experiments or observations. In 1930, a German philosopher named Karl Popper noticed that it was not in fact the verifiability, but it was its very falsifiability that made a statement scientific. In other words, the practice of using experiments is not to verify, but to refute the scientific theories to establish the basis of true science. This is in sharp contrast to the common view that science is based only on empiricism through inductive reasoning and experimental verification. This principle of falsifiability has been accepted for hypothesis formation and testing in modern science. His famous example was the statement that all swans are white. This statement would be accepted as true as long as no black swan is observed. Unless falsified, a scientific statement is accepted to be true. However, this does not mean that it is absolutely true, because it can be revised due to the fact that our observations are always fallible. A second important criterion of a scientific explanation is called parsimony. 13th century British philosopher William of Ockham states that to explain a phenomena, we should prefer The simplest description is possible among various explanations. This is also known as Occam's razor. For instance, a mathematical model with the lowest number of parameters is always favored. Therefore, scientific inquiry, with the possibility of being verified or falsified through observation and experiment, is the only objective account of an event. This assumption offers a privileged status to scientific knowledge against other forms of knowing. We can talk about three levels of representations in society only granted to science. One of them is the knowledge claims of scientific experts in public discussions. The other is the expert witnesses specialized in scientific fields testifying in courts. And finally, the privilege granted to scientific research to access to the privacy of the individuals. How did science attain this privileged status in the Western societies? The status and fate of science is itself something non-scientific. It is a unique combination of cultural and institutional factors. It is an interplay of non-scientific domains of culture. From a sociological point of view, the value of scientific truth is not derived from nature, but it is a product of definite cultures and institutions. What do we mean by that? For the last 5 centuries, individuals living in diverse countries contribute to the advancement of science. It is a transnational activity having an intellectual continuity against geographical, cultural, and linguistic diversities. Such things as certain metaphysical assumptions, canons of evidence and proof, rules of etiquette and reciprocity, all form the ethos of science. We can talk about 3 basic factors which provide science such a sociological status in society. First of all, we have to talk about the existence of a publicly recognized social role called scientist, who teaches and produces scientific results, transmits and diffuses the knowledge, and helps the formation of a scientific tradition. The other 2 factors are the social norms and the existence of communities with values. Now, what do we mean by social norms? Robert Merton proposes 4 sets of institutional imperatives associated with scientific activity. The first one is called communalism or sharing. Scientific discoveries do not belong to one person, they belong to everyone. Scientists should share their results openly through talks and publications so that everyone can learn from them. The second one is universalism or fairness. Scientific work is to be judged only by its quality. It shouldn't matter who the scientist is, where he or she is coming from. Everyone should have an equal chance to contribute. The third one is disinterestedness or honesty. Scientists should work to find the truth, not to get rich or famous. They should keep their personal biases out of their research. And final one is organized skepticism or questioning. Scientists should not believe new ideas immediately. Every claim must be carefully tested and checked using logic and evidence before it is accepted as true. There are also other norms as individualism, originality, rationality, etc. The ethos of science is the spirit or culture of science. It is made up of the values and commitments that scientists agree to follow. From a positivist worldview, the history of science is believed to be linear, accumulative, and progressive, leading to the human thought approaching closer to the absolute truth. In the 1970s, Thomas Kuhn, in his famous book, The Structure of Scientific Revolutions, came up with an alternative model for the history of science, challenging the positivistic, linear, progressive model. Thomas Kuhn regards the history of science as a series of revolutions instead of linear and progressive steps, and he uses a key concept called paradigm to explain his model. What is a paradigm? A paradigm is a theoretical or a methodological belief that permits selection, evaluation, and criticism of the facts. Students study these paradigms to become members of the particular scientific community and to practice science. People whose research is based on shared paradigms are committed to the same rules and standards for scientific practice. Paradigms are used for creating lines of inquiry, formulating questions, selecting methods, defining areas of relevance, and sometimes establishing meaning among observations. A paradigm is essential to prioritize the facts to explain a scientific phenomena. A paradigm can be created by collecting mere facts and finding out different descriptions and interpretations. Pre-paradigmatic schools, emphasizing a special part of the collection of facts, start to emerge first. From the competition of schools, the best paradigm singles out by explaining the facts, making research possible. A paradigm transforms a group into a profession or at least a discipline by promoting the new paradigm through journals, professional societies, academic culture, etc. History of science, according to Kuhn, is a cyclical process. During normal science periods, a paradigm cherished by the scientists yields successful results, extends the knowledge, and articulates itself further. A certain time passes, and after that, the paradigm starts to fall short to explain some new cases called anomalies. During this time, the paradigm starts to be questioned but not abandoned. When the anomalies accumulate, they create a crisis. This indicates the failure of the existing theory. A crisis period can terminate in three different ways. It can survive by finding a way to handle the crisis-provoking problem. This means that the problem stays, but it is perceived as a result of technical insufficiencies which can be solved when necessary tools are developed. The second way out is the emergence of a new paradigm which explains the anomalies and replaces the old one. This is a scientific revolution, which is not a cumulative development, but a completely new set of definitions, concepts, and tools replacing the older one. To give an example, although Einstein mechanics may reduce to Newtonian solutions in macroscopic world, Newton defines mass as constant, whereas in Einstein it is a function of velocity. We can say that normal science is cumulative, but scientific revolution is not. New paradigms arise with destructive changes in beliefs about nature. When we reject a paradigm, we reject its fundamental assumptions and its way of doing science. Therefore, we can also abandon the belief that a paradigm change is necessarily moving us closer to the truth. A typical historical example is the Copernicus theory of orbits. Up until the 17th century, almost everybody was accepting the geocentric theory that the sun was revolving around the earth. Copernicus challenged the idea that it was in fact the earth that was revolving around the sun, which we call the heliocentric system today. Despite oppositions, of course, slowly people began to accept this new theory. In fact, Copernicus's theory started a new period of normal science. For another example of a paradigm shift, we can turn to the 20th century and look into the acceptance of Einstein's general relativity to replace Newton's account of gravity. When a particle moves with a speed close to the speed of light, Newton's theory of motion becomes insufficient to explain the behavior of the particle. In such a case, mechanics of Einstein is used. Popper's principle of falsifiability and Kuhn's non-cumulative paradigmatic explanations of scientific history ushered in a new era that we call post-positivism. According to this updated version of classical positivism, the world may not be knowable in its absolute sense because it is ambiguous, complex, variable, and multiple in its realities. Researchers acknowledge that they are, to some extent, bounded by their values, admit that they have biases. They sometimes even benefit from their subjectivities during this research process. Methods are often inductive, moving from particular observations to broader generalizations. Scientific truth, is value-bound and limited by its presuppositions, rather than universal and eternal. Scientific endeavor based on the senses like intuitive, metaphorical, and creative can also be equally legitimized as appropriate ways of knowing and exploring the world. A scientific problem needs to be understood as a holistic structure where the whole is often more than the sum of its parts. Findings sometimes may be unique to the study problem and context, therefore not suitable for generalization, but they may have their own intrinsic value so that the lessons learned from one context can be applicable to others. As an example, let's assume that a student explores whether recycled water could be used to irrigate bananas. In the first phase, the hypothesis is that there will be no biophysical differences between bananas irrigated with town water and those irrigated with recycled water. She accepts the positivistic assumptions, conducts her research according to the rules of scientific method, and confirms her hypothesis. In her second phase, she explores whether consumers would buy bananas irrigated with recycled water. In her surprise, many consumers still show reluctance to purchase these bananas, although they believe that there is no difference in quality between irrigated and recycled water producers. She needs to go post-positivist to draw conclusions that are seen as both credible and valuable by realizing that truth and reality can be two different things. Therefore, the aim of our doctoral training should cultivate a researcher in a dual character, a specialist as well as a critical thinker. Research is not just an experiment. It is thousands-year-old conversation about knowledge, reality, and our place in the universe. It's a dialogue between the dead and the alive. Scientific progress requires more than specialists. It requires researchers who really understand how science works and who can bring in critical thoughts from other domains of knowledge. How can we do scientific research? First of all, it requires us to know and observe some set of rules. We follow these rules to plan, conduct, analyze, and report scientific knowledge based on ethical principles. These rules are defined as research methods. We must start by stating a clear question, a problem, or a purpose. Then we must describe a systematic process to be implemented so that our findings will be valid, replicable, and reliable. We have to explain the methods, the data, and the analyses clearly. We also have to follow the ethical principles, which require informed consent of human subjects, avoiding any harm to participants, honest reporting, and proper attribution of intellectual, financial, and institutional contributors. We must critically analyze the assumptions, methods, findings, and identify the limitations of our study. So if you make a start to a journey for your research, these are the fundamental steps of research methods, which we hope to talk about more in other lectures in this series. Thank you.